The second subproblem in object category recognition is detection. And for detection, we will actually look at two different approaches. One of them is sliding windows, and the other one is generalized Huff transform. So let's start with the sliding window approach. The main idea in the sliding window approach is to use a binary classifier. So the basic component is a binary classifier that, for instance, looks at this image here and decides whether this is a car or not. So it gives a binary answer. If I feed in another image like this, it will actually tell me whether it's a car or not again. And the sliding window idea is that the object can be anywhere in this image, and the image is supposed to have some background, so we expect some clutter. So the idea is actually I take a patch of certain size and I slide through the image, testing every possible patch in the image with my binary classifier to decide for each patch whether there's a car or not. And I basically do it for varying sizes of patches to gain some sort of robustness to scale differences. Obviously, this is a brute force approach with many, many local decisions. Now notice that here I can actually use any type of classifier like the ones that I've seen before using the bag of words. Now, again, fleshing out this pipeline a little bit better, what we do is we first obtain a training data. For example, if I'm actually interested in detecting cars, I create a training data set of cars and non-cars. And this presence of the negative example is very important to be able to decide whether there is no car in a certain scene or not. Then using these examples, I define certain features and I train a classifier. The classifier gives decisions in the local patches. When a new test image comes in, I slide my window all across the image, and for each patch, I decide whether there is a car or not. Now, as I said, ideally, I can use whatever I've seen before. I can use, for example, the specific object recognition ideas that I've seen before, using the reverse index trees, inverse indexing, or I can use the ideas with the bag of words. And these are all fine. However, the point is, I need to make a lot of decisions. So I need to make, for every patch, a binary decision. So that basically means that, for example, if I'm using bag of words approach, for every patch, I need to extract the bag of words representation. And that actually might be costly. So alternatively, I can look basically for easier features to extract. So let's actually discuss a little bit what easier features there can be. And actually, the modern detection algorithms indeed use easier features instead of the bag of words. And don't get me wrong, to basically identify the entire scene and to understand or summarize the entire scene, bag of words is still extremely useful. However, for the detection part, using simpler features might actually yield more efficient algorithms. So what can be the simplest features? I can basically, for example, look at the grayscale or color histogram, so a simple holistic description of the image content that's obviously much easier to extract than bag of words. I can even say, for instance, you know what? Maybe I can just vectorize the entire image, pixel by pixel, and use that as a representation. Now, these are both a little bit not well thought. So the pixel-based representation is obviously extremely sensitive to small shifts. So even if I actually have a very small shift in the image, the entire representation will be different. So I will not be able to do a matching accurately. On the other hand, the color or grayscale-based appearance descriptions on the histograms, well, they might be sensitive to elimination and intra-class appearance variations. For example, I wouldn't be able to find an albino koala if I assume that the koala color should always be gray. Instead, the gradient-based representations really have a certain advantage. Specifically, we can actually consider the edges, and we can look at the orientation characteristics of the intensity gradients. And I'd like to remind you that actually when we discussed feature extraction 2 weeks before, we also talked about the gradient-based representation being extremely robust, and we've seen that actually it's been used in the most popular or most useful feature extractors like SIFT or SURF. In particular, we've seen that actually the histogram of gradient orientations or histogram of oriented gradients to be a particularly useful representation when it comes to SIFT. And in most sliding window detection-based approaches, it is still a choice of representation, histogram of oriented gradients. So just to remind yourself what that means, that I basically divide the patch into several regions, and within the regions I extract histogram of gradient orientations, and I use the gradient orientations to basically as features which are fed into a classifier to do a detection. And it summarizes local distributions of the gradients, so it's locally orderless. It offers invariance to small shifts and rotation. And the contrast normalization is, well, it tried to correct for variable illumination patterns by normalizing the contrast in the images to get the best histogram orientations. And indeed, there are quite successful detection methods that use hog representations, so histogram of oriented gradient representations, for various applications. For instance, here we see a result for the pedestrian detection. And detection here is obviously made for each window of different sizes. And we see that there are certain cases that it's actually extremely successful. There are certain cases that actually misses the pedestrian, or basically they cannot really evaluate or distinguish between two individuals here. And there are obvious cases of false positives that are detecting pedestrians as non-pedestrian. And this is obviously because it uses histogram of gradient orientations as a feature descriptor that cannot make a distinction between this figure here and this figure here. Okay. Now, another way to actually use sliding windows is to use another set of features that are actually even simpler than the histogram of gradient orientation. So when you think about it, the histogram of gradient orientation actually assumes a certain pattern in the image. So it assumes that it's a little bit handcrafted. It basically puts a lot of emphasis on a certain type of feature. Instead, what we can do is, instead of extracting or being clever in extracting features, we can basically extract very simple features, but a lot of them. And for any specific task, we can ask the classification algorithm to decide which features are useful, and simply use these features in building a binary classifier. And in that case, the rectangular integral image filters are particularly interesting. The features are very, very simple. So they're basically rectangular filters that looks at differences between the intensity patterns or intensity averages in different areas in the image. The feature output is really difference between the adjacent regions. So in this case, for example, this feature looks at the intensity difference between the area that's indicated white block here with the black block here. This actually looks at the difference between the white block and the two black blocks, and so on. Now, these are obviously very simple features, and actually computing them can be done extremely fast using what's called an integral image. So integral image basically finds that, you know what, I basically take an image here and I compute the integral or basically integral at each point. So at point xy, the integral image simply represents the integral of all the intensities to the left and above this x and y pixel. So for a given image, if I can actually construct an integral image like this, then computing any integral feature, like the ones I've given here, I basically can be done in constant time by simply reading off values and subtracting simple intensities in the integral image itself. For instance, if I want to compute the difference between, or the integral between in the image D, I can simply use the values at 4, 2, 1, and 3 in the integral image to compute it. So actually the area in D simply corresponds to the integral of the intensity value of the integral image at 4 and 1, subtract the integral image at 2 and 3, and there I will basically get the area of D. So you see that it's actually just reading of intensity values of the integral image to compute the sum of intensities of a very large area in the image. And that's pretty neat. and actually avoid and you know that actually if I actually scale the image or get a larger area or a smaller area, it doesn't really matter, because even if I increase the size of this d, the cost of computing the integral is exactly the same. So that's pretty neat. Okay, so one example of an integral image is given here. So for this image right here, the underlying integral image can be given as the image that's given with the jet color map here underneath. So if I want to compute the integral image feature, the difference between these guys, I simply have to read off 6 values in the corners right here, and basically adding and subtract them in the correct order, I will get the difference between these two different areas very fast. Now the idea is, these integral features, or the integral image features, are extremely easy to extract, but they all look a little bit, in a sense, not extremely informative. So the crucial idea here is to say that, you know what, I know that each feature here may not be informative, but if I can extract lots of them, so consider all possible filter parameters in all positions, scales, and types, then I can actually create maybe a set of features where an algorithm can identify the correct or a useful subset among these features for any classification task. In practice, we create a very large library of filters. So for any given image, I extract even hundreds of thousands of features. And then I need a classifier to select the informative ones. And obviously, again, I'm repeating, not all of them will be informative. Now, among the classifier choices, we can actually use many classifications. However, when we actually talk about these integral features, and when we talk about we need to find or select a subset of features that are informative, then actually algorithms that fall in this class of boosting or random forests have a clear advantage. They can actually determine the relevant features automatically for a given task. And we'll talk a little bit about one of the algorithms that's actually made a big splash in computer vision, which is the ADA boost. The idea about boosting is that we build a very strong classifier that can really detect whether a car is present or not very accurately, for instance, by combining many weak classifiers, which only need to be better, a little bit better than pure chance. If I actually put such classifiers one after the other, in the end, I will get a strong classifier. So it's a sequential learning process. At each iteration, we're going to add a new weak classifier. And it's flexible to choice of weak learner, including fast, simple classifiers that alone, again, may be inaccurate or slightly better than pure chance. So in particular, as I said, there are many ways of doing this, but we'll look at the Freund-Shapiro's ADA boost algorithm that's easy to implement, and actually it's the base learning algorithm for one of the most successful face detector in computer vision, which is the Viola and Jones face detector. So what's the intuition between the ADA boost? Now let's assume that we have a simple problem with two-dimensional feature space. So I have the positive examples that are shown with the red dots here, and I have the negative examples that are shown with the red dots here. I want to create an algorithm that will actually classify these samples perfectly. Now, a weak classifier can be described as simply dividing this entire feature space into two, basically getting a classification accuracy of at least 50%. Okay? So I will have misclassified samples in this case, right? For example, my first weak classifier is this guy, and I noticed that it actually divides the red from the blue samples. So somewhat okay, but it has some errors. In the next step, when I want to add a new weak classifier to this, I simply upgrade the weights of the misclassified ones and find a new classifier. Again, it has to do a little bit better than the chance. Now, when I combine these two, I see that actually I get a classifier that's quite accurate. It only makes one mistake in the red class and no mistakes in the blue class. So by combining the two weak classifiers, I get a stronger classifier. So the algorithm in length is actually a bit lengthy. So given a set of examples, we basically apply exactly the same procedure over and over again. We find weak classifiers, we start with a uniform weight on the training examples, and find a classifier, evaluate the errors, weight the samples that actually had errors in them, so reweighting the examples of the incorrectly classified ones, and creating yet another weak classifier. And the final classifier, as I said, is the combination of the weak ones, weighting according to the error that they had. Now, this other boost algorithm, we don't have to go through detail. I think it's important to understand the intuition behind it, and I strongly recommend going over it, but we don't have to know it by heart. But it has been the underlying learning algorithm for one of the most, as I said, important face detector algorithms in computer vision, which is the Viola-Jones detector. So this algorithm is actually for frontal faces, and it combines the global appearance models with a sliding window detection approach. It basically uses a regular 2D structure, and the idea is that the center of the face is almost shaped like a patch window, so it covers the entire face. Okay. Now let's see how the other boost is used, and let's see how the Viola-Jones detector actually makes use of the other boost algorithm. So as we said, it creates a very large library. So for each image, for each patch, it extracts many different features, and it uses other boosts to select the informative ones and to form a final classifier. So we want to select the single rectangle feature. So what is the weak classifier choice for the Viola-Jones detector? We want to select a single rectangle feature and threshold that best separates positive, meaning faces, from negative, meaning non-face images in the training examples, and in terms of taking into account the weighted error. So for example, if I look at this feature here, this feature will have a certain response from all the samples. And actually, this will have a one-dimensional scalar response. So in a sense, I can actually put the outputs of all the samples of this feature in a single line. What I want is a threshold here that will separate the red and the blue samples as good as possible. Then I will look at another feature and then at another feature. So the idea is I want to choose, I will try many different thresholds and choose the threshold and the feature that gives me the best separation at that point. For example, this feature will give me the best separation with this threshold. And that will be my first weak classifier. In the next round, I will compute the errors this weak classifier makes, reweight the samples, and find another feature with another threshold to append to this weak classifier. So in this case, each image feature will correspond to a weak classifier. And for each round of boosting, I will evaluate each rectangle feature on each example, sort the example by filter values, select the best threshold, meaning the minimum error, considering the weights. And this actually can be done simply by sorting and quickly scanning all the optimal thresholds. Select the best filter and threshold combination, weight this feature based on the error rate, and reweight again. Now, extracting so many features from all patches might still be quite expensive computationally. So even if each individual feature is fast as compute, I have to evaluate a lot of them. So how can we actually make it a little bit more efficient? And the crucial idea here is to use a cascade of classifier of increasing complexity. So basically, the first classifier is not a very strong classifier, but it's able to get rid of many of the patches in the image, saying that they don't have a face. The important point is this classifier does not get rid of any patches with faces. So it actually has no false negative, but very small number of false positives. The next one is a bit more complicated classifier, getting rid of more of the non-face patches and the next classifier is even more complicated, getting rid of even more of the non-face patches, in the end leading to actually a strong classification that's composed by basically putting together the entire cascade. So if there's a face, it will actually fly through all the classifiers as saying that it includes a face. If I have a patch that actually looks like a face, it will pass through the first simpler classifiers, but at some point a complicated classifier will say that this is actually not a face. And if I have a patch that's clearly not a face, it will be actually discarded even in the first runs. So this way, I don't have to extract many features from all patches in the image. Basically, initial non-complex classifiers may be using very few number of patches. So cascade of classifiers can actually, cascade of classifiers of increasing complexity can give me a lot of efficiency. So wireline face Jones detector, basically the summary is I have a large training data set of faces and non-faces. I train a classifier using the integral image features using AdaBoost. And basically, AdaBoost algorithm select the features and weights them. And I create a cascade of classifiers that actually will go through each patch in the image. And in the sliding window approach, we'll find the face or multiple faces in the images. What they did in this algorithm is that they trained with 5,000 positive and almost 350 million negative image patches. And using the cascade classifier, they could actually achieve a real-time detector that in the end, the very complex classifier uses almost 6,000 features in the final layer. So imagine that actually using 6,000 features for all the patches would take time, but using the cascade, they were able to reduce the computational cost quite a bit. Now, the two features that were selected predominantly using the AdaBoost that were really useful for detecting faces look something like this. And if you actually put these features on an image or a patch containing face, you'll exactly see why. You see that actually this feature looks at the difference in the eyes, and this feature looks at the difference in the eyebrows and the rest of the face. So they're actually really face-dedicated features in a sense. And the speed, as I said, at testing time, it was extremely fast. It was able to detect faces at 15 frames per second on a conventional PC of the time, so 2001. The down part, or maybe not the down part, but the interesting part was the training time took weeks. And this is, by the way, is not extremely uncommon in machine learning. Even today, to create very complicated models, you can actually take a number of days to create really strong algorithms. So let's see some results of this algorithm. It was able to actually extract the faces even when there are multiple of them and at different scales. Because the algorithm is fast, I can run it in different scales. I was able to find, despite the variations in skin color, it was able to find despite the variations in illumination. It was even able to find despite extremely large scale differences. And notice that there's some interesting parts here that it's not able to detect the face here because the File and Jones face detector was trained for forward-looking faces. So whenever you have a face that's not forward-looking, because it didn't see it in the algorithm, it didn't see in the training examples, it's unable to detect it. Some more examples, again, showing extremely good results, actually being able to detect most of the faces, as well as some non-face patches that looks like faces, and very few errors overall. And again, what we see here, in some of the cases, maybe it's using the glasses quite accurately to identify the faces, while if it actually has a face that's really not frontal looking, it makes an error. So the wireline face detector was a huge success. It's actually the first real-time face detector available in computer vision, but it was weak on non-frontal faces. And whenever there was strong expressions, it made error. And there are many derivative works and improvements over the wireline-Jones detector. And there is actually a C++ implementation available that's in OpenCV that you can actually try right away. So the idea about the sliding windows is, let's have some final remarks about sliding window detection. The advantages are you can actually create a very simple detection protocol and you can actually implement it in a simple way. Good feature choices are critical. Again, we cannot really extract extremely complicated features because it will take time. But you cannot actually extract bad features because then you'll get a bad detector. But this is actually a part of the process, especially if you think about Weil and Jones. There are a lot of successes for certain classes, especially face, and there are very good detectors available. The limitations are it's still high computational complexity. So for each patch, you need to detect. You need to give a decision for each patch. So more than 100,000 locations in an image has to be fed through a binary classifier for basically a decision. Now, this puts a tight constraint on the classifiers that we can use. We cannot use extremely complicated classifiers. If training biodetectors is independent for different classes, this means if I have, for example, if I'm interested in detecting multiple objects in the image, then I need to train multiple binary classifiers. That actually costs both in training time, but also in test time, because I have to run them successively. One can actually try, for example, a generic object detector in the sense like I don't necessarily detect a specific object like a face, but any object, and then running a more specified object detectors only in those regions to maybe reduce the cost. But the idea is with so many windows, the false positive rate has to be low, and the sliding window approach typically needs fully supervised training data. That basically means that there's lots of images and bounding boxes that identify the objects of interest in the images. Some limitations are we are well aware that actually while faces looks like box-shaped patches in the images, most of the objects are not box-shaped. If I look at the train, for example, the geometry here, it doesn't fit in a box. If I look at, instead of a face, but a human body, obviously different parts with the different deformations, it doesn't look like a box at all. Different objects of interest can be actually non-rigid, meaning that they can deform, and deformations are not very well captured with the boxes or the sliding window approach. The representation assumes a fixed 2D structure or a fixed viewpoint. That's a big limitation. Objects with less regular textures cannot be captured very well, especially with the holistic appearance-based descriptors. And basically, when we apply sliding window approach, we basically take windows and basically slide them through the image and give decisions for each window independently. That basically means that the context is completely lost. Actually, if I take this image and simply shuffle all the patches, the detection results of this image will be roughly the same as the detection result of this image. So that's actually a big limitation, that it actually completely ignores the context and looks at the windows in isolation. Again, in practice, creating such good algorithms often entails extracting very large training sets, manually cropping windows that actually might be expensive, and it would really require good matching to a global appearance. For example, if I have such partial occlusions, then I will have some troubles if my training data set does not include examples like this one. So even though it's actually kind of looks at the patches in the sliding window approach, it resembles or it uses the ideas of global appearance features in a sense, and not the local appearance features that might be useful to get rid of or to tackle the occlusion problems. While sliding window is extremely useful, generalized half transform actually improves on these limitations quite a bit. So the idea about the generalized half transform is that it's an implicit shape model. The basic idea is that we learn an appearance codebook and we learn a star topology structural model. So features are considered independent given the object center. So the algorithm that we construct in the end is a probabilistic generalized half transform. So visual vocabulary is used to index vote for object position, meaning that if I have this image, for example, the idea is that if I can detect the wheels of this car, that detection can tell me where the center of the car can be. So in a sense, for instance, I wouldn't know if this is the front wheel or the back wheel, but it doesn't matter because I can simply say that, you know what, let's encode with this wheel two directions that are possible locations of the center of the car. So whenever I see this visual code word, this visual code word will encode a displacement vector to the center. So by doing this, I can simply go through the image, run my detector, find the wheels, and each wheel basically give me two directions. And the idea about the implicit shape model or general self-transform is to simply create a voting. For example, in this example, for this location, there will be two votes saying that this is the center of the car, while this location and this location, there will only be a single vote. Same as here, at this point, there will be two votes, while here and here, there will be single votes. So by looking at the points in the image that achieve the highest votes, I can actually identify the centers of objects. And if I can identify the centers of objects, that basically means that I can actually detect the object in its entirety in a much faster way. And note that the interesting part is I didn't do any sliding window approach. Instead, I always talked about the code words, which basically means that I could use the visual words idea here to detect the wheels, and then the wheels will tell me where the center of the object is. So that's a very different approach than using sliding windows object detection. And like that, I can actually use the entire tool set I've created with the visual words and the vocabularies. So I have my training images, and from the training images, I extract the object centers and different parts of the object with different scales. Using these patches, I create appearance code books, for instance, using the visual words approaches that I've seen before. And then for each code word, I learn a spatial distribution. So I match code book to training images and record the matching positions on the object. For example, in these cases, for the center of the body here, I record where this patch is positioned with respect to the entire object. In this case, it's always the center. If I look at the feet, it's actually positioned always at the front. If I look at the head, it's positioned always a little bit above from the center. And if I actually look at the structures here, it can actually either be a face or it can be down here. The feet can be down there. So it's actually the spatial occurrence distributions that corresponds to each code book that I record. During recognition, instead of going with sliding windows, I simply find interest points, and from each interest point, I match to the codebook entries, so find the words that correspond to these interest points, and each word will basically now point out or give votes to different pixels in the image of what the center of that object should be. If I'm actually looking to identify human bodies, then in this case, these parts of the human bodies will basically give lots of votes to different areas. And I already see that actually some parts of the image receive higher votes. So in the 3D voting space, in the continuous case, I basically, just like I would in the Hoff transform, I find the areas with the highest vote. And once I have the highest votes, I basically identify the location and the scale and back project based on the assumption that the center of the object is here or here, back project where the other parts of the object should be, and using the best probability hypothesis, I can actually construct a bounding box around the object of interest. Let's see some examples with the chairs, which are actually very well structured images. I can see that given images like this, the generalized Hoff transform and the implicit shape transformation is able to really identify the objects quite well. Despite the variations in the chairs, partly because similar parts are shared across all chairs. And the chairs themselves have very well structures. Okay, Now, the Unix libraries or the code for this is also available, and you can actually try it home quite nicely. And some final remarks about implicit shape models as well. So the advantage is it works very well for many different object categories, both rigid and articulated objects, as long as they're somehow well structured. The constellation is stable. It can actually create flexible geometric models. So combine parts seen on different training examples together. It has very good properties in terms of dealing with occlusion and clutter. You can actually learn such models from surprisingly few training examples. And it's really optimized for detection with very good localization properties. The disadvantages, it still needs supervised training data. So you need object bounding boxes to do any detection to learn any model. And it might even be useful to have segmentations for top-down segmentation. So if I'm really trying to identify different parts of the object, then I would really need bounding boxes on those different parts. And it only actually yields very weak geometric constraints. So results, after the results, my actually segmentation may contain superfluous body parts. For example, if I identify that for this case, for this test image, the center of the object is right here, then based on the center, if I can actually recreate possible segmentations of the object, I see that actually for some cows with the center, they had 2 legs here. So in the reprojected hypothesis, I will have 2 different legs at the center that should not be there. And with that, I will end today's lecture. And thank you very much.